Yes, welcome to Unit 12, Lesson 5. It's about fission, fusion, and transmutation. We're going to discuss the differences between the two and the advantages and disadvantages of using fusion. These are all energy sources. Our note packet today will be going through 12 through 14, and our practice packet will be doing pages 13 through 15. All right, let's go ahead and begin. This is going to be on page 12 of the note packet. So if you can go ahead and get there, we'll go ahead and begin. So, artificial transmutation. Well, artificial transmutation means the changing of an atom into a different element. So we usually do that by changing the nucleus, bombarding the nucleus with a high energy particle, such as a neutron or alpha particle. Nuclear fission. This is the splitting of a nucleus of an atom. If it's a large particle, we'll split it into smaller particles. For example, a nice slow neutron colliding with uranium-235 will form, among other things, barium and krypton elements. Completely different elements, therefore transmutation, and transmutation in different elements. Okay, I think I went over this before, so I'm going to go on to, I think I covered this, guys, the last time. So we talked about how this energy isn't just a one-to-one ratio, so it just gives us a steady flow of energy. Nuclear power through fission creates a chain effect, so that it multiplies with every collision. You get more and more product, which includes energy and heat, which is why weapons can be made using nuclear fission, but also it is can be used for power. The disadvantages of fission is that the chemicals or the isotopes you create emit dangerous radiation, so radioactive waste. Also produces a ton of energy. I mentioned thermal pollution. Okay, let's move on to page 4, where we'll talk more about fusion. And this was in the news recently because fusion is a source of a tremendous amounts of energy. The energy that's really is found in the sun. So you can take lighter, more stable nuclei like hydrogen, trillium, and deuterium are isotopes of hydrogen. Combine them to get helium, isotope 4, and a neutron, and lots and lots of energy, which again is our source. Now, we recently, saw, I think it's the Lawrence Livermore Lab in California, they produced for the first time more fusion energy than they took in to make the process happen, which was very unique. And so maybe within our lifetime we might get fusion power plants. They're a lot more safe than the fission that we talked about before. So there's a bunch of different examples of the way we can combine basically hydrogen isotopes to form different hydrogen isotopes or helium isotopes and create energy. There's many advantages of fusion. There's lots of energy, significantly more energy than fission can produce. There's no nuclear waste, so that's ideal. Examples, the sun uses a fusion reaction to create energy. Cold fusion, human attempts to harness the fusion of an energy source on Earth. This is what we're trying to do at earthly temperatures, not the temperature of the sun. The disadvantages of fusion so far is that we need to overcome the extreme energy barriers. So it does take a ton of energy to create a fusion reaction. Difficulty to control the reaction once it's accomplished. We think that is a difficult thing, and I should link a video on that. Maybe we'll watch it sometime. Now notice that massive amounts of energy is produced as a product in both fusion and fission, but where does the energy come from? The idea is it comes from the binding energy, which we aren't super clear about, but that binding energy between protons and neutrons. So there's a tremendous amount of energy that holds on to the nucleons, protons and neutrons, so tightly together. That energy is released whenever a nuclear reaction or rearrangement occurs. How do we know that it exists? Well, it comes down to Einstein's equation, but the total mass of the products are less than the original mass, so we've noticed a small mass defect. During a nuclear reaction, a certain amount of matter is converted into energy, and we estimate that to be based on Einstein's equation that the amount of energy lost is equal to the mass lost times the speed of light squared. So when particles of matter are made to vibrate at the speed of light squared, they are converted to energy. So this is the foundation of our nuclear industry, I would say. So moving on. The combination of these two phenomena is what accounts for the massive amount of energy released during fission and fusion. Okay, we're almost done. I know it doesn't seem like much, but we're going to introduce half-life. The half-life of a substance decays is how long it takes to decay and is not dependent on any other factors. So this is important because when you look at half-life, in a chemical reaction, it usually depends on temperature, pressure, and concentration. But half-life for nuclear reactions is independent of all of them. So no matter where you store a nuclear device that's slowly decaying or material, it will decay no matter what outside forces that are acting on it. It is impossible to predict when unstable nucleus will decay because it's a completely random process. The only thing that can be determined is the number of unstable nuclei that will decay in a given time. So we can't tell you exactly when a particular neutron will unstabilize itself in the nucleus, but we can determine over a given period of time how much of it will. Therefore, half-life, or the time it takes for half the mass to decay, is a very important concept under nuclear chemistry. Note that half-life varies per substance, and so every different substance can decay at a different time. So I think I mentioned at the very beginning how fast calcium-37 decays. It just takes 175 milliseconds for half of the sample to displace or to be decayed. And that is extremely fast. So before 1 second occurs, nearly 99% of the material will be decayed. Now basically, the shorter the half-life of an isotope, the less stable it is. The longer the half-life, the more stable it is. All right, we'll get more into half-life, but I'd like you to turn to the practice packet. And the practice packet, pages I'd like you to work on are pages 13 to 15. And I'd like to at least a couple of problems with you and walk you through those. The first one is, in which type of reaction do lighter nuclei combine to form a heavy nucleus? Okay, so we just went over this one. I'm hoping you recall that it's nuclear fusion, because that's when the hydrogen and so forth get combined. Which substance has a chemical property similar to radioactive U12L5? Now, if they said nuclear properties, that might be something different. We look on table N, but it said chemical properties. The things that share chemical properties are the same element, so only look at the same element. So that would be uranium. Given the diagram represent this reaction, which phase best describes this reaction and overall energy that change occurs? Okay, not a bad problem at all. The neutron is coming in. The neutron hits the uranium-235 it looks like split into two different daughter atoms, and those isotopes that are created release also two neutrons. So in this case, this is a pure nuclear reaction and energy is released. Hopefully you recall that this is nuclear fission because it's breaking apart of two particles. But it's nuclear and energy is definitely released. Which term identifies a type of nuclear reaction? Reduction? Nope, that's for redox reaction. Neutralization, that's acid and base reactions. Deposition, that's for solubility of materials. Transmutation. All right, I might do a couple other ones, maybe number 10, which change takes place in nuclear fusion reaction? Ionic bonds, nope. Matter is converted to energy, that looks good. Energy is converted to matter, that looks good. Covalent bonds, nope, that's the chemical reaction. So we're looking for nuclear. Let's look at these B and C more closely. Matter is converted to energy. That looks familiar because we talked about E equals mc squared. Energy is converted to matter. We've never talked about that. This would be really interesting. We have not talked about out of nowhere creating matter. That's a whole different cup of tea. All right. So it is option B if I haven't mentioned that. All right. So, guys, I want you to work through these. I know it doesn't seem like enough work and you'd really like to have more work. I just need you to work on up to page 15, which is problem 27. Okay, this will get you well prepared for the test. Now, tomorrow we'll go over half-life, which is our last unit of study. And you can see we have a lot of work. So if any of you want to work on that early, that's completely fine with me. But I'll go over it in the notes tomorrow. I'll see you then. Thanks for your hard work.